Thank you. So let's move on for our next presenter. It's Connor from the Department of Geography in London, UK, UCL. London, be my guest.
Connor, you're on mute.
We cannot hear.
Connor, you're still on mute.
Yes.
Yep, there we go. Hi, yeah.
Oh, yeah.
I'm Connor Barker. I'm working as a postdoc with Professor Eloise Murray at University College London, and my research has been looking at ozone depletion and climate forcing from satellite megaconstellation emissions, so the modern space industry, and where megaconstellations like Starlink and OneWeb come into those environmental impacts. So the sort of main impacts of the space industry come in two areas. They come from the launch emissions and from the re-entry emissions. So launch emissions are emitted over the sort of the whole atmosphere, which makes them quite different to surface-based emissions from something like cars or factories or aviation, because they're emitted throughout the troposphere, throughout the stratosphere, even throughout the mesosphere, and then higher. The type of emissions from these depend on the type of propellant used or the type of fuel used by each rocket stage. So these propellants can either be hydrogen, kerosene, which is refined jet fuel, methane fuel, which is a new fuel being used by rockets like Starship, which you may have seen recently, the impressive videos of them blowing up, impressive and scary videos, and then hypergolic fuel and solid fuel. And the main emissions from all of these are water vapor, but there's also some thermal NOx. This comes from the hot rocket plume traveling through the atmosphere and oxidizing nitrogen, ambient nitrogen in the atmosphere to NOx. There's also some fuel NOx from hypergolic fuel. Chlorine and alumina are really destructive for ozone, and those are released by solid fuel. And then also from kerosene and methane, we get carbon emissions like carbon monoxide, carbon dioxide, and black carbon. There's the launch emissions. We also have re-entry emissions. Again, we have thermal NOx. This comes from as the hot object re-enters the atmosphere, it burns up the atmosphere as it re-enters and creates NOx emissions. So you get this from all re-entries, regardless of the type of re-entry. And also metal oxide emissions. As these objects enter the atmosphere, they often break up, and they're often designed to break up as much as possible so they don't hit things on the ground. And this releases metal oxide particles into the atmosphere, but we don't really know what these particles look like yet, or the size of them, or their optical properties, or their chemical properties. So that's a big area that we need experimental data on in the future. And the re-entering objects can be anything from payloads like satellites, components like the rail the satellite is deployed upon, capsules containing cargo or people, also reusable rocket stages like the first rocket stage of the Falcon 9 rocket that lands at the spaceport or on the ocean barge, and also debris. There's a lot of debris in low Earth orbit that falls down as well. The main impacts of these are stratospheric ozone depletion and climate forcing. So stratospheric ozone depletion is mainly driven by NOx and chlorine. There's a previous study in our group that looked at the impact of a decade of increasing 2019 rocket launch and re-entry emissions on stratospheric ozone and climate. And it found that about 50% of the ozone depletion was from NOx and about 50% from chlorine. There's a smaller percentage that's from alumina, water vapor, and black carbon. For alumina and also for stratospheric liquid aerosol of any kind, there's also some small ozone depletion where particles act as a surface for ozone depletion, a heterogeneous surface. So when you release metal oxide particles into the stratosphere, the mesosphere, these act as a surface for ozone depletion as well, but this is a smaller effect than NOx and chlorine. There's also additional black carbon impacts that come from the warming of the stratosphere by black carbon absorbing shortwave radiation, and that can lead to changes in stratospheric dynamics and also influences on the rate of ozone destroying reactions. So in addition to those, so stratospheric ozone depletion as well, globally, it's small compared to surface sources. However, the loss in the Arctic specifically could be a reversal of about 10% of the recovery we've made from the Montreal Protocol. So it's worth thinking about in the near future, because this is an industry that is directly depleting stratospheric ozone. As well as this, there's climate forcing. This mainly comes from black carbon absorbing solar radiation, but there's also a small effect from alumina reflecting solar radiation and also absorbing terrestrial radiation. And this is all occurring quite high up in the atmosphere. So compared to particulate emissions in the troposphere, these are black carbon particles being released above the tropopause mostly, and absorbing energy in the stratosphere, warming the stratosphere. And this is much more efficient at warming than, say, black carbon emissions from aviation. So black carbon emissions from the space sector are 375 times more efficient than surface sources at warming the atmosphere. So what's changed since this previous study in 2019? Well, one of the things has been the onset of the satellite megaconstellation era. So there's two main satellite megaconstellations at the moment. These are the SpaceX Starlink constellation and the Eutelsat OneWeb constellation. SpaceX has launched over 8,000 satellites, with 1,000 of them re-entering already. OneWeb is about 600 up and 6 down. And these satellite megaconstellations, or SMCs, are contributing to rapidly increasing launch rates and re-entry mass. There's currently around 7,000 to 8,000 objects in low Earth orbit at the moment, orbiting Earth. About 75% of these are from satellite megaconstellations already, and they were only started launching in 2020. So this is quite a big contributor already to the number of satellites in orbit. And there's currently nearly 8,000. There's planned to be another 60 to 100,000 in the next 2 decades. So this is going to be a huge increase in mass going up into orbit, and then mass re-entering the atmosphere as well. More than 1 million satellites have been filed to be launched. But it's debatable how many of these actually get launched. So this is what we wanted to really study. What are the impacts of these megaconstellations specifically on the environment? Because this is a massively increasing sector. And there's also been a sort of increase in the understanding of emission chemistry. So we now know that the launch emissions change with altitude depending on the oxygen availability. So there's a certain set of emissions that come directly from burning the fuel. These come out of the engine of the rocket. These are stoichiometric emissions, and these are independent of the altitude. There's also secondary afterburning emissions. These depend on the availability of oxygen in the hot oxidizing rocket plume environment. And these are extremely complex reactions, but we can try and model these using emission indices, so grams of emission per kilograms of propellant burned. Try and model those and create an altitude profile. We also know from some recent data that was taken on a NASA aircraft campaign that 10% of aerosol particles in the stratosphere contain metals from spacecraft re-entry. So we know that when these particles are being released by rockets and re-entry high up in the atmosphere, we know that these aerosol emissions are eventually coming into the stratosphere and being taken up by stratospheric sulfate. And we know that's going to have interesting impacts on chemistry in the stratosphere, but also interesting impacts on radiative properties of the atmosphere. The coating of black carbon, for example, will have an absorption enhancement effect, leading to an increased absorption by black carbon in the stratosphere. So what we wanted to do in this study was put these emissions into a model and understand their environmental impacts. So we used the GeoSchem chemical transport model, with a resolution of 4x5 times 47 layers. 0 to 80 kilometers covers around 80% of the launch emissions. And we couple this with a radiative transfer model to understand the radiative impacts. We input into this offline meteorology and a whole host of other emission inventories. But what I've been doing for the sort of first year and a bit of my postdoc was creating an emission inventory for space industry emissions. So there's kind of 2 parts of this. The first one is to model launch emissions. To do this, we combine a literature profile of the propellant consumption with altitude with emission factors that are altitude dependent. So this takes into account the afterburning emissions that I spoke about earlier. You can see an example here for a Falcon 9 rocket. This is the rocket that launches the Starlink mega constellations, and it's the most used rocket by far in the world. you can see the altitude range that the geochem model covers, and also that the first stage of the rocket operates over. So we're covering all of the first stage of this rocket, a little bit of the second stage, and we're also covering the re-entry emissions from the rocket coming back down, first stage of the rocket coming back down, and then the landing emissions as well. And we do this for all rocket launches from 2020 to 2022, and make sure that we have the sort of best understanding of where these emissions are being inputted, and when. We noted that annual propellant consumption increased from 36 to 63 gigagrams or kilotons in 2020 to 2022. So this is a massive increase in just a few years. We combine this with re-entry emissions. These are higher up, 60 to 80 kilometers. We split the objects into different categories to better capture the emissions from each object. Unfortunately, we don't have detailed information on all re-entering objects, such as the velocity or the shape of that object, or any sort of individual plume modeling analysis, but we do have an idea of what the mass of that object was and what the emission factor of that would be. We did this for all re-entering objects in 2020 to 2022, and we found that the re-entry mass is now about 40% of the natural influx from meteorites. So we're getting to a stage now where the amount of mass coming down from humans is similar to the meteoritic contribution. And we also noted that about 2 kilotons of unabated mass is returning to Earth and hitting the surface, and this number is growing every year. So the amount of mass that's actually not breaking up in the atmosphere and hitting the surface is increasing, which is also quite worrying and could be a bigger impact in the near future on things like air traffic being diverted, people being affected, or sort of property being affected. So we compiled this emission inventory for these 3 years. This is an idea of the vertical distribution of these emissions. So this is just for 2022 and shows the proportion of emissions that are emitted at different altitude bins up through the atmosphere. And you can see that, for example, for re-entry emissions, these dominate in the mesosphere. So the blue on the left-hand side, this is NOx emissions very high up in the atmosphere. And also alumina emissions are being emitted mainly into the mesosphere. And also black carbon, BC, is being emitted, mostly being emitted in the sort of upper stratosphere, lower mesosphere. We also see that the contribution of megaconstellations to re-entry emissions is increasing yearly as well. So these megaconstellations are becoming a bigger and bigger fraction of emissions in the modern space industry. So we take our emission inventory, and for 2020 to 2022, this covers the kind of onset of the megaconstellation era, and we project these numbers to 2029. You can see the projections in the bottom left in terms of rocket launches and re-entries a year. So currently in 2024, there was nearly 300 rocket launches. There's probably going to be more than 300 this year if the trend continues, or maybe the year after that. So we're getting near to the 1 a day range now. Same with number of object re-entries. The numbers sort of growing linear every year. And we put those in the model and do simulations with no emissions, all missions, including all megaconstellation missions and all non-megaconstellation emissions, so we can see the impact of each. And then we look at the impact on atmospheric composition and radiative forcing. We had to make quite a few changes to the model to look at this. So we had to add metal oxide as a new aerosol species, add some new gravitational settling to this, and also, as I spoke about before, add the uptake of particle emissions to stratospheric sulfate into our model, which was quite a tricky thing to do because GeoChem is a model that uses externally mixed aerosol, and we're kind of trying to approximate internally mixing that aerosol in the model. And we needed to include as well lensing effects. So these are when a non-absorbing shell coats a absorbing core, like black carbon. So in this case, it would be sulfate coating black carbon. You get an enhancement in the absorption of the black carbon because of the lensing of the light, focusing the non-absorbing shell focuses the light onto the core, essentially. This is what this slide shows the changes in stratospheric concentration across the decade for our emissions, with all emissions shown in blue. So this is every single rocket launch and re-entry. And then in orange is just the magaconstellation mission. So that's where the launch contained a satellite that was a magaconstellation, so Starlink or OneWeb, or the re-entry was something to do with the magaconstellation. You can see that for the top left with ozone, there's ozone depletion globally in the stratosphere of about 0.03%. Now, this is quite small compared to surface sources, which is about 2%. So it's still quite small, but it is growing. And this is expect some other studies that have looked at future scenarios have suggested it could get up to 2% in the future. What is interesting is we can see that for the magaconstellation only one in orange, there's very minimal ozone depletion. And this is because magaconstellation launches primarily use kerosene fuel. About 98% of the propellant consumed for magaconstellation launches is from kerosene fuel. And this releases very few chlorine or NOx emissions, which means that we're not emitting a lot of ozone depleting emissions for SMC launches. On the right here is a graph that shows the stratospheric liquid aerosol concentration in the atmosphere, and shows that stratospheric liquid aerosol, or sulfate aerosol, is concentrated in the lower stratosphere. So we uptake our particulate emissions of alumina and black carbon to stratospheric liquid aerosol, and we can see that this essentially removes the aerosol from the atmosphere and sort of seasonally, and then increases again. So you get this effect where it's almost eliminated once a year, and then rises and falls. If you compare this to a simulation where we don't include this uptake, we've reduced the concentration of these emissions by about 98%. So really, this is a big impact on our simulations. So was just speaking about uptake of particulate emissions by stratospheric sulfate. This is what the annual mean aerosol concentration looks like for black carbon and alumina. So in our model, black carbon is very small. This means that when we release these particles high up, the black carbon stays for a long time. So it settles extremely slowly. And it means that you get this very slow increase and decrease in concentration in the mesosphere. But you don't see any concentration increases in the mid to lower stratosphere. And this is because as soon as the particles get there, they get taken up into sulfate. For alumina, the same thing happens, but the particles are usually a lot larger, and this means that they more rapidly settle. But the concentration increases are still limited to the mesosphere and upper stratosphere. But what we do see is that there is an increase over the decade in the surface area of stratospheric liquid aerosol. So stratospheric sulfate particles, the surface area of these particles is growing over the decade. This provides a bigger surface for ozone depletion, essentially. So there is a kind of secondary effect where we sort of enhance ozone depletion by increasing the surface area of the stratospheric liquid aerosol. One of the uncertainties in this work is what do the particulate emissions look like in terms of alumina particles. We know what the particles from launches look like because we have some studies on the space shuttle, but we don't really know what the particles from re-entry look like because we have no experimental data. Launches suggest that about 8% of the particles are submicron, but we don't really know. So we did a sensitivity simulation to see what would happen if we made all of the particles submicron instead. This would mean a lot more of them stay in the atmosphere and would have a bigger impact on ozone depletion. And what we actually saw was that there was almost no global change in ozone. The percentage change was extremely small, but the location at which that ozone depletion occurs shifts towards the mid stratosphere. And this is very preliminary, but we think this is a shift away from ozone depletion occurring from on the surface of sulfate particles and towards it occurring on the surface of alumina particles themselves. I know we're close to the time, so I'll go through this one quickly, but we essentially put our also look at the relative forcing in the model. So we look at the relative forcing this is just 2022 for now, but what we see is that there is an overall warming of the stratosphere and a cooling of the troposphere. And this comes from black carbon absorbing shortwave radiation in the stratosphere before it has a chance to get to the troposphere. There's also a small effect from ozone depletion. So as ozone is depleted in the stratosphere, there is kind of less forcing from the ozone that's there. So that has a kind of opposite impact to the black carbon. And there's also a small reflective effect by an increase in stratospheric sulfate, increasing reflectivity of the stratosphere as well. So just to summarize, we've sort of developed emission inventory and we've looked at the impacts of those. We've also recently been building some emission trackers for rocket launches and re-entry. So the bottom two QR codes there will take you to those on the group website. So that's a kind of visualization of our emission inventory for those years. So yeah, thank you very much.
Thank you for the presentation, Connor. This was very interesting. I can say for myself personally, I have never thought about this before. Most of us are so focused on, like emissions from the ground that, yeah, I never thought about what would happen up there. I have a question for you before opening. Just you mentioned that there are some future scenarios that say that the depletion will also will reach the ground ones quite soon. Do you have an idea how soon? Are we talking about decades? Are we talking about centuries? Is there a time scale for that?
I think those future scenarios tend to use quite extreme scenarios. So they predict quite a large increase in rocket launch and re-entry rates. It really depends on how many of the proposed constellations get built. There's currently 2, Starlink and OneWeb, really. But there's Amazon is launching one. The Chinese government are launching 3, I think. There's a Russian one. The EU is launching one. There's several more American ones. And there's so much kind of funding going into this that it could be a lot quicker. We could start to see exponential growth in these launches and re-entries very soon.
Do we have questions? More questions?
We do. Yeah. First is a long one. So from Sachin, mesosphere is one of the coldest layer of the atmosphere. So considering this, if we frame a hypothesis that whatever gases are emitted get condensed into the solid phase, this can be seen in the increase of the black carbon concentrations as compared to other layers of atmosphere. But we see that NOx concentration is also high as compared to other layers of atmosphere. Please provide your thoughts.
Yeah, I think, well, I mean, where the increase in concentration happens is really as a result of where the emissions are released by the rocket. So, for example, the reason that there is a lot of black carbon emitted high in the atmosphere by the rockets is because there's not a lot of oxygen available the higher up you go, which means that when in the rocket plume, there's less oxidation of the black carbon into carbon monoxide and oxidation of the carbon monoxide and carbon dioxide, and you get more incomplete combustion, which leads to more black carbon higher up. So it's more of a function of the chemistry of the emissions. For that, I'm not exactly sure how the model deals with. I don't think there's any sort of partitioning of black carbon between solid and liquid phases in the model. I'm not sure. Yeah, it's something to think about. In terms of sort of mesosphere mesosphere emissions, one of the things that definitely I haven't looked at, but other people are looking at, is ice nuclei. So we know that if you're going to release a lot of water vapor and particulates into high up in the atmosphere, you might start to get interesting cloud formation that wouldn't otherwise be there, because we're putting a lot of emissions into places where you don't usually get those type of emissions. So yeah.
Okay, thanks. There are two more questions. One is from Adi. Could you elaborate? Could you please comment on stratospheric black carbon re-radiating long wave radiation back to the Earth's surface? Doesn't it increase the radiative forcing overall?
Yeah, so the overall effect to the atmosphere is to warm the atmosphere, but it will be a warming of the stratosphere and a small cooling of the troposphere. In terms of long wave, the results I've got so far show that short wave is a far bigger component than the long wave, but there will still be some long wave effects in there. It's just that the short wave absorption by black carbon is so dominant over all the other effects that that kind of is the story really at the moment. So yeah, long wave is there. It's just dominated by short wave.
And Ishur comes with a geochem related question. Could you say a little more about the resolution dependence of such high altitude emissions? Because your model is based on 47 layers and not the 72-layer version.
Yeah. I mean, it's something we've thought about, and I am running simulations to look at the impact of this, because we're running for 10 years with these emissions and doing such a kind of different number of simulations at the same time. We've stuck with the 47 layer, but it may be that we have to look at the 72 as well.
Great, thank you.
I would like to thank you all. Thank you very much, Mahinder and Connor, for the availability. In case anyone still have more questions, please direct them to the presenters, or share with us, and we can forward to them. So in the chat, you can see some links. So we have monthly newsletter. We have seminars like this every 2 months. So if you'd like to show your